Good day, good people. Let us look at chapter 7, column and struts. I want to believe that you've already went through the column and strut, and we are done with chapter 6, and we are okay with it, and we can answer any question regarding chapter 6. Now, uh, this coming Sunday, the president will be talking. We don't know if we will be going back or not. And if we are going back, we still have to hear what is the Minister of Higher Education is saying, if they will postpone the exams or not. If they will not, or if obviously they will postpone the exams, because the exams are supposed to start on the 23rd. That gives you the picture that if we will be opening, we won't have time. We will have to write test 2, and we will have to prepare for exams. Please do your work, good people. If you have any question regarding the activities or regarding the topics that we dealt with, or you are even ahead of me in terms of the topics, please let me know so as to help you, or else you will find yourself being left out, or rather not qualifying to write the exams. Having said that, let's look at chapter 7. On chapter 7, we are dealing with column and struts. Né? A long column or a strut is defined as a member where length is relatively long compared to its cross-sectional area. And we all know that the column, they are defined in the column. You can tell that the length, it is greater than what the cross-sectional area. On the previous topics that we dealt with the beam on the horizontal position, whereby we determined the critical point of the beam, and whereby we determined the critical point of the beam in a form of your bending moment. We determined that critical point of the beam, and the critical point of the beam, you can tell that it is caused by the direct stress, or it is the bending stress. It is the bending stress. Then on the other topics, we dealt with the face of that critical point. What's happening when the force has been applied? What's happening to the face of that critical point? But on your column and strut, we will be dealing with your beams standing vertically. So on this chapter, we are dealing with beams, or the same beam, this one, but now standing in a vertical position. That's what we will be looking at. We'll be examining what's going to happen to this beam when the force is being applied. Now, when the force is being applied directly on this column, there are a few things that you will be realizing. Now, when the force is being applied directly, the beam, it will bend. This beam, it will bend. The length would be affected. Right, let's continue. A long column subjected to a load. A long column subjected to a load will buckle, or it will bend in the direction in which it is the weakest long before the material has reached its elastic limit. Now, in short, the beam will buckle or bend on its weakest side, and the weakest side of the beam, we know it is the longest side, and the longest side, it has to do with the IYY. That's what that statement simply says. When a long column buckled or bends, the load applied can be calculated by using Euler crippling theory. When the long column buckles, the load applied can be calculated, meaning the load applied, the force applied, this force applied here, can be calculated using the Euler theory, or using the Euler theorem. When the force is being applied and the beam buckles, bends, we can calculate this force using the Euler theory. And what does the Euler theory says? The Euler theory says the stress in the column due to direct load. Due to direct load, this would be the direct load, is small compared to the stress due to the buckling failure. Ne? The stress that will be caused by this, it is smaller comparing to when the beam does what, fails or breaks. That's what the Euler theory says. But in our course, we don't look into the Euler theory. Instead, we are looking at the assumptions, and of which the assumptions in your books regarding your Euler, they deal, with part of what the Euler theory is saying. And like your beam has to be homogeneous. We know that when the beam is homogeneous, what does that mean? Those assumptions that he states, that the axial load has to be applied in the cross-sectional area of the beam and so forth. Now then the buckling part of it will take place and so forth. Those are the part of your Euler theory. But the long columns, in short, they are using what? Euler theory. The long columns, or rather the buckling load, it is determined by using what? Euler theory. Now the short columns, and of which it is this one, the short columns, they are using the rankine theory, or rather we are using the rankine theory to calculate the force applied when the columns are short. When short columns are used, where the material is crushed or crumbled rather than buckling, the load causing failure is determined by what? By rankine. By rankine. Now when you were doing your N4, we dealt with two things. We dealt with the elongation percentage, if you would remember, and of which we do have it in chapter 1. In chapter 1, elongation percentage. I know that you don't even remember the formula of elongation percentage, but we'll deal with it when we are doing chapter 1. Then we have reduction percentage. We have the reduction percentage, because your strength, it is based on chapter 1, chapter 2 and chapter 3. That which we are doing in chapter 1, 2, 3, it deals with your strength throughout. Reduction percentage. Elongation percentage, it deals with the length of the beam. It has to do with what? With the length of the beam. Then reduction percentage, it has to do with the cross-sectional area of the beam. That when the force it's been applied, or more especially the tensile force it's been applied, then the length of the beam will be affected. Whether a tensile or compressive, the length of the beam will be affected. Now we get to realize that the length would be either increased or decreased. Now on the reduction percentage, we said it that the reduction percentage, it mainly looks at the effect of the cross-sectional area as a result of the applied force. When the force it's been applied, what's going to happen on the column, on this short column? When the force it's been applied, the column will buckle this way, meaning the cross-sectional area would be increased. Now this is the part that we dealt with in N4 and chapter 1, chapter 2 and chapter 3. In this case, when the force it's been applied, you can tell that your beam will bend sideways. Your beam will bend sideways. This beam can bend in a sideway in such a way that it is no longer going back to its shape and size. Then when we measure by how much did it increase, you'd realize that it will have increased by a certain percentage, or the length has been affected by this much or by the certain percentage. You can tell it's just a continuity of what we did in chapter 1, chapter 2, but we haven't dealt with it in N4, when we're doing our N4. Now Strut, it deals with short columns, and we are using rankine to determine struts. Then Euler, it uses it worked, or rather Euler, he looks at the long columns. What's going to happen when the force it's been applied on the long columns? Né? That's what Euler deals with. The force that needs to be applied, né? Or rather this buckling force. Né? That's what Euler he's all about. Rankine, short columns, he as well look at the buckling force. Rankine, buckling force, but on what? On the short columns. That's what we'll be dealing with on your chapter 7. But how they bend, meaning these columns, the long column and the short column, how they bend, it depends on how they are fixed. How these things bend, how this cross-sectional area or short column being affected, it depends on how they are fixed. Let's look at the fixing of those beams. How columns buckles depends on how they are fixed. Right. Fixing of the ends. Now, number one, both end fixed or built in, né? Meaning both ends are being fixed. You can have the fixing in this way, né? This gives you the picture that these beams are being fixed on the wall. Fixing, they are being fixed, right? Both ends, they are being fixed. Effective or bowing or bending length equals to 0.5 of the original length. Now effective length would be 0.5. Now the effective length, good people, it deals with the affected length of the beam. It's a long column beam. Now we look at where will this beam be affected. If this beam is affected just here, where it's been affected, it is called the effective length. Oh, what did I do now? Right. Where this beam it's been affected, it is called what? Effective length. That's what we are checking when the load it's been applied on the beam. The length of the beam, is it affected holistically, or it is affected 50% of the original length is been affected, or 70% of the original length has been affected? That's what effective length is all about. Now you can tell that when both ends are being fixed, the beam will be affected at the center, because we are told that effective length equals to 0.75 of the original length. That gives you the picture that if they are both ends being fixed, when the force load is being applied, 50%, half of this would be affected, or rather that's where the buckling, the wobbling will occur here. The bending will occur. Why it will occur there? Because both ends are being fixed. That's where the wobbling or the buckling will take place. That's what it simply means. That means on your Euler formula, when both ends are being fixed, you will use the effective length, or rather you would use the length or the part of the length that is being affected as this formula here, as this. Right. Now let's look at both ends being pinned. They can either use the word pinned or hinged. They can either use the word pinned or hinged. Hinged. Now when both ends of a beam are being hinged, it's like ufagama pin lapha phezulu man on the ends, or your ufagama rivets, or in Slogish they would say witekile, with welding. Now when both ends are being hinged or pinned, you'd realize that the force applied here, it will cause the beam to wobble, and from the point of hingement to the other point of hingement. That is why the effective length, or the length, would be affected holistically. So that is why effective length equals to L. meaning effective length or the affected length, it is the same as your original length, meaning the beam will be affected holistically. The whole length of the beam will be affected when both ends are being pinned. Then one end fixed and one pinned. When you are having one end fixed, in this case it is pinned, then this side it's been fixed. Now that gives you the picture that when they applied, or when the load it's been applied, the quarter of this beam will be affected. Can you see that? 0.707 multiplied by original length. Effective length equals to 0.70 of the original length. Now when one end fixed and one pinned, this is the formula that you need to use on your length, because this gives you the picture that the length of the beam, it will be affected from that point to that point, and we are told that it is only 0.707% of this that will be affected. That will be affected. Now when applying the formula, your LE would be 0.707 multiplied by the length of the beam, right? Then let's look at one end fixed and the other end free. Effective length equals to twice the original length. Twice the original length. You can tell that if the force it's been applied on the beam where the one end it is fixed and the other one it is free, they are saying it is twice the length. That means the effective length, how this thing will be affected. This thing can bend till, right, you can tell, hence they are saying it is twice. It can be affected from there to the other side. Now this is the formula that you'll be using. LE equals to 2 multiplied by original length. Now let's look at those formulas, the formula of Euler and the formula of Rankine, so as to see where we applying this LE. Now like I said that Euler, he deals with long columns. This is the formula of Euler determining the force applied on the long columns. It is force equals to pi squared multiplied by E for Young modulus, then the I for least moment of inertia, the IYY, then the effective length that we were dealing with. Now that which will indicate for you the value of effective length, it is how your beam it has been fixed. Now let's say it is 50% a buckle, meaning both end they are being fixed. That means your LE, the value of LE, it will be 0.5 multiplied by, let's say the length of the beam it is it is 4. That means your LE it will be it will be 2. Then here you'll be having 2 squared on your LE. You'll be having 2 squared. It will be pi multiplied by the value of Young modulus multiplied by the least. And the least, if it is not given, the least, you must always calculate it. How do we calculate the IX, the IYY? How do we calculate it? We know how to calculate the IYY if it is not given, or if we are not referred to use the periodic table, we know how do we use it. It is D B cube divided by 12. If we are given the square, the rectangle, bars and whatsoever to work on them. If we are given the round bars, we know that we have to use I, because IYY and IXX on the round bars, they are the same. It is pi, right, 64 multiplied by d quad. It depends. If it's a solid, it will be, or if it's hollow, it will be something like this. If it is it is hollow, you'll be having something like this. Then if it is solid, then it will be divided by by, is it 32? if it is solid. This is the formula that you'll be using in determining the IYY. It will depend what beam are you given in calculating, so as to be able to calculate your I. The good thing is that we dealt with the IYY, how to calculate the IYY. Now the strut or short column or the rankine formula, that which will indicate for you that you have to use the rankine formula, it is the rankine constant ratio. This will indicate for you, if you are given the equation, this will indicate for you that you have to use the formula of rankine. But please, on your LE, the LE, whether it's rankine or whether it is Euler, it depends on the fixing of the beam. It depends on the fixing of the beam. It depends on the fixing of the beam. It depends on the fixing of the beam, good people. It depends on the fixing of the beam. LE, it depends on the fixing of the beam. It doesn't matter whether it's rankine or Euler, it deals on the fixing of the beam. Right, it deals on the fixing of the beam. Now on rankine, this is the formula that we'll be using to determine that buckling load or buckling force, using rankine formula. But that which will indicate for you in most cases that you have to use rankine, it is the constant ratio. If your equation, if the given equation, you see the rankine ratio there, you know that you have to use rankine. But if you can check the formula of rankine, it considers the ratio because the cross-sectional area would be affected. Like I said, elongation percentage and reduction percentage is just the continuity of those theories that we dealt with in N4, and that which we'll be dealing with in chapter 1, chapter 2 and chapter 3. That's what we'll be mainly dealing with on the column and strut. Then I will be dropping a video on the application of it. We'll be doing activity, is it activity 7.1 number 1 as our example. Thank you, good people. Please make sure that you study.